Hey Team GChem, and welcome to today's lecture, where today we're going to continue our discussion of chemical nomenclature and how to name compounds. And so today's learning goal is going to involve a bit of review about what we discussed last lecture, naming binary compounds, but we're going to add on to that discussion of binary compounds a little bit more in depth, and then we're also going to talk about how to name polyatomic compounds. So those compounds that have 3 or more elements. And so as you watch through today's lecture, pay attention to the different categories we're going to discuss. We're going to talk a little bit about covalent versus ionic compounds, introduce this topic of acids, talk a little bit about naming organic compounds, and then talk about some of the memorization that you're going to have to do as you learn this topic. So with that, let's get started. All right, so in class, I introduced to us this flowchart that I find really helpful in thinking about how chemists use slightly different naming schemes depending on what type of compound we're talking about. In particular, if there's a metal or another type of polyatomic cation, like NH4+, the ammonium cation in the compound, then we know we're dealing with something that's an ionic compound, and we're going to name it a certain way that's slightly different than if we're talking about a covalent compound. And so while this is going to be a review for many of us, let's go through 2 examples of dealing with binary compounds to start off with. First with a covalent compound, and then with an ionic compound. So here's an example of a compound, ClF3, that we need to figure out how to name. And the very first thing we want to do is we're going to pull up a periodic table and try and figure out whether or not these elements that are present are metals or nonmetals. And so you'll see that there's a periodic table to the lower left of your screen, and Cl is element 17, so that's part of my nonmetal category, and then fluorine is element 9. It's also a nonmetal. And so I know that this compound is going to be a covalent compound, and the way I'm going to name it depends on a little bit on what elements are present. Since I don't have to deal with hydrogen in this case, I'm not dealing with an acid, something we haven't talked about yet. And so what I can do is notice that there's 2 elements present and name it according to the rules for binary covalent compounds. If you remember our rules, we need to know what the prefixes are so that we can explicitly state in the name the fact that there's 1 chlorine and 3 fluorines. And so for our naming scheme, what we're going to do is indicate the prefix for the chlorine, except that because there's 1 chlorine, we get to eliminate the prefix mono in this case. Otherwise, it's a little bit redundant. So we're going to say chlorine instead of monochlorine. And then the second element, we're going to give its appropriate prefix, tri in this case. And instead of saying fluorine, we're going to change the suffix to "ide." So what we end up with for this compound's name is chlorine trifluoride. So that's what we do if we're dealing with covalent compounds. And if we're dealing with ionic compounds, the naming rules are similar, but a little bit different. In this case, with MgBr2, I see that there is a metal present in the compound. Magnesium is element 12. It's to the left of the periodic table where the metals live. However, magnesium is not a transition metal. And so the type of ionic compound I'm dealing with is an ionic binary compound, where what I'm going to do is name the metal first, and then name the nonmetal second, and again, change that ending to "ide." That's going to give me the name magnesium bromide, and you'll notice that the difference between my covalent compound naming scheme and my anionic compound naming scheme is that with covalent compounds, I have to include the prefixes to say how many of each element there are, whereas with my ionic compounds, I just need to give the names and change the suffix of the second element to "ide." Now, to give one more example of these binary compounds, once we're dealing with a transition metal, transition metals we know have variable charges associated with them. And so we're going to have to include as part of the name what the charge is on the cation. So for Fe2O3, again, notice that iron, element 26, is part of the metals area of the periodic table. And because it shows up in that kind of rectangular long block where the transition metals live, I know that iron is a transition metal. And so the type of scheme that I'm going to use to name this compound is that I'm first going to name the transition metal, iron, but now I have to figure out what the charge is. There's many ways to figure out what this is, logically, but one way that I like is if you've practiced the crisscross method for figuring out how to put together a cation and an anion to form a compound, you can use sort of the reverse crisscross method to figure out what the original charges must have been. So in this case, the subscript 2 next to the iron tells me that the charge on oxygen was 2-. I sort of already knew that because of oxygen's location on the periodic table. But the 3 next to the oxygen tells me that iron's charge must have been a 3+. And so now I'm ready to name this compound. Because I know that iron's charge is 3+, I can go ahead and call this iron 3 oxide. Now, some of you in the room may have named this compound slightly differently. It's equivalent and perfectly fine to, instead of calling this compound iron 3, to instead call it by its more common or historical name, which in this case would be ferric oxide. And so with that, we've gone through a couple different examples of using this flowchart that are hopefully for us somewhat familiar compared to our last lecture. In addition to these covalent and ionic compounds, there's also typically special naming rules for organic compounds. This is a whole class for organic chemistry, and so in general chemistry, we're going to give you just the briefest introduction to a couple of organic compounds called alkanes that we want you to know for this class. Our organic compounds, I want you to notice that all of these alkanes look like we might have 10 different things to memorize, but in fact follow a pattern that helps our memorization. All of these alkanes have a particular molecular formula where there's a certain number of carbons, and then the number of hydrogens is twice that many carbons plus 2. So for example, the alkane that has 3 carbons has 8 hydrogens because 3 times 2 plus 2 equals 8. So when we're naming our alkanes, the only thing we have to do is say how many carbons are present. And so for our purposes, you'll notice that the prefixes that tell us how many carbons to expect are very similar to what we used for our inorganic covalent compounds. The only ones that are a little bit different are, you'll notice that instead of mono, we have meth. Instead of di, we have eth. And instead of tri, we have pro. So we follow Greek prefixes for this instead of the Roman prefixes. And that can be a little bit confusing, but it's something that we just have to get used to as chemists. All right, so that almost takes care of all of our compounds that we need to deal with that have 2 elements. We had a little bit of review from the ionic and covalent compounds, and then these organic compounds should feel new to us from this lecture. The last category that we need to talk about are acids. We're going to talk a lot in general chemistry about what is an acid and how does it react chemically, but for today's lecture, the only thing I need you to know is that acids are molecules that have 1 or more hydrogens, and in fact, H+ ions that are attached to some anion. And what will happen is if you put this acid in solution, it means it gets to act as an acid. Binary acids are named differently depending on whether they're in water or not in water. And so as an example, let me talk you through HCl. If HCl is listed without any indication of what phase it's in, or if you see a parenthesis G to the right of it that tells you that it's in the gas phase, we're going to name this based on rules that should start to feel familiar to us from ionic compounds. HCl becomes hydrogen chloride. Again, we're naming the first element, naming the second element, but changing the suffix to "ide." If, however, this acid is in solution, we use a slightly different naming rule to remind us that this acid is going to dissolve in water to release H+ ions. And so, in fact, what we're going to call this acid is hydrochloric acid. So the pattern that you'll notice for these binary acids is that we put the name of the element, put the prefix hydro in front, and the suffix ic acid afterwards. So a couple examples of this that you might see is, for example, HBr with the symbol AQ next to it to say that it's an aqueous solution or it's dissolved in water would become hydrobromic acid. HCN, we'll see in a second that Cn- is a polyatomic ion called cyanide, so that would become hydrocyanic acid. And then last but not least, H2S would be hydrosulfuric acid. All right. It wouldn't be a language learning experience if there weren't a couple of exceptions to binary compounds. And so on this slide, I've given all of the exceptions and common names to expect for binary compounds. Some of these may feel pretty familiar to you. For example, you probably are used to calling H2O water in your life and not the standard name of dihydrogen monoxide. So these common names show up in chemistry, and it's pretty typical for us to call B2H6 diborane, CH4 methane, NH3 ammonia, etc., because these are common names that were given to these compounds prior to chemists adopting a more universal systematic way of naming our covalent compounds. Similarly, the stock system of naming transition metals, for example, iron 2, iron 3, was developed after people had been using kind of common names for many of these transition metals. And so iron, copper, lead, and tin sometimes are called either us or ick type ions to indicate the lower and higher charges that chemists have seen. And so the correspondence between those is that the us indicates the smaller of the two charges that you would see for a transition metal, and ick indicates the larger charge. But knowing what charges show up, for example, the fact that lead could either be a 2+ or a 4+ cation, is a matter of memorization. And so many of these naming exceptions you're going to want to put into flashcard format in order to practice. All right, so that takes care of our discussion of binary compounds. And now we have an opportunity to start thinking about polyatomic compounds, compounds that have 3 or more elements. And what we're going to talk about next are a couple of common use cases for these polyatomic compounds. We'll talk through oxoacids, common polyatomic ions that you should expect to see and will unfortunately have to memorize, and then we'll talk about oxoanions and hydrates. So let's get started on that subject. So, polyatomic species. There is a table in your textbook, table 2.5, that has a full listing of polyatomic ions you need to know for chapter 2. And it's a lengthy list that I highly encourage you not to just blindly memorize. So on this slide, I've shown you what, in my opinion, is the list of polyatomic ions that you do have to memorize. And it's kind of a complete list. So these are the types of polyatomic ions that don't follow a set of systematic rules, and so you kind of just have to memorize them by flashcard. However, a lot of the items on table 2.5 are ones that you can know through pattern recognition and through these systematic naming schemes. So for example, if you have an ion that has only one element, normally like we practiced last lecture, you can use the periodic table to figure out what its charge should be. So as an example of that, we would see that magnesium, which lives in the second column of the periodic table, is going to have a +2 charge because that's the charge that elements in that group always have. Similarly, although the rules are going to be a little bit more complicated and we're going to have to talk about them, polyatomic species that have oxygen as one of the elements present, which are going to be called oxoacids and oxoanions, also follow a set of rules. So if you can learn the rules, it's going to cut down drastically on the amount of memorization that we have to do. So let's start off with oxoacids. The definition of an oxoacid is a ternary acid. Ternary means that the acid contains 3 elements. And in particular, those 3 elements are hydrogen, oxygen, and something else, which can vary. Acid means that it's a compound that starts off with the element hydrogen. And like we saw earlier, and like we'll go into detail in more later in the semester, an acid means that it can lose hydrogen from the compound in the form of H+. Unlike oxoanions, which we're going to discuss in a moment, oxoacids are neutral compounds. So we don't need to worry about them being anions or cations. They're always going to have a charge of 0. So let me give you a couple examples of oxoacids, and these ones are the ones that you're going to have to memorize. And I'll show you in a moment how all other oxoacids and their names are derived from these 5 sort of reference acids. What's really important in your memorization is to pay attention to what's the element that's not hydrogen and not oxygen, and then secondly, in that reference compound, how many hydrogen atoms are present and how many oxygen atoms are present. So for example, we have a formula H2CO3. This reference acid is called carbonic acid because carbon's present. And you'll notice that there's 2 hydrogen atoms in this compound and 3 oxygen atoms. Again, this is a table that you're going to want to memorize because all other oxoacids are named with respect to these reference acids. So here's how you name oxoacids in general. Once we have memorized or have reference to this list of, standard oxoacids, we can name any other oxoacid based on a comparison between how many oxygen atoms your acid has that you want to name versus how many oxygen atoms the reference acid has. Let's do an example so you can see how this works in practice. So if I have an acid, HClO4, I'm going to look at that acid compared to my reference acid. I see that chloric acid, HClO3, has 3 oxygens, but HClO4 has 1 more than that, 4 oxygen atoms. So my naming rules are that because I have 1 more oxygen atom, I'm going to put the prefix per in front of the name chloric acid, but I'm going to keep that ic acid suffix. And so HClO4 would be named perchloric acid. Here we have 2 more examples that I want to go through, H2SO3 and H3PO2. Go ahead and pause the video and see if you can use the 3 rules that I've listed on this page for naming to figure out what the names of this should be. Once you've paused the video, go ahead and answer this and then restart once you're ready to see what the answers are. Okay, so for H2SO3, I look once again at my reference acid, in this case sulfuric acid, and I see that my acid that I'm interested in, H2SO3, has 1 fewer oxygen atom compared to sulfuric acid. So my naming scheme is going to be the root, but I'm going to replace the word ic acid with the word us acid. And so I'm going to end up with sulfurous acid instead. Similarly, for H3PO2, I see that compared to phosphoric acid, I have 2 fewer oxygens. And so I'm going to name this hypophosphorous acid. So again, depending on how many oxygens I have compared to my reference acid, that's how I know how to name these derivative oxoacids. Once I know about oxoacids, I can also start to think about oxoanions. Oxoanions are polyatomic ions that are formed by removal of at least 1, but maybe even more H+ cations from an oxoacid. So one example of how an oxoacid could form H+ and an oxoanion is if we take something like H2CO3, which if you started to pay attention to our reference acids, is called carbonic acid. So if carbonic acid leaves behind an H+, well, that electron that we lost from H+ has to go somewhere, and it stays behind with the oxoanion. And so what we'll be left with is HCO3-. So notice this pattern. In our oxoanions that we're about to start naming, every missing hydrogen leaves behind a single negative charge on the oxoanion. If we took away a second H+ from HCO3-, we'd be left with CO3-2-. And that's going to be important in just a moment because it's going to help us figure out both the formulas for these oxoanions and what their names should be. So naming oxoanions is something that's going to take a little bit of practice, but it follows a very systematic set of rules. And once again, our reference table of oxoacids is going to help us name these oxoanions, and it's going to help us determine their charge. So the rules are going to be that anytime we want to name an oxoacid, we're going to start off with a prefix that tells us something about the number of hydrogens present. Then we're going to add a prefix that tells us something about how many oxygens there are relative to the reference acid. And then kind of just like with our oxoacids, we'll have the root word that describes what that third element is. And then maybe there'll also be a suffix related to the number of oxygens that are present. These oxygen rules are very similar to how we named oxoacids. The per and hypo prefixes are identical, relating to one more oxygen for the per prefix or two fewer oxygens for the hypo prefix. However, you'll notice that the suffix changed. Now, if we have the same number of oxygens as our root acid, instead of saying ic acid for our suffix, we're going to use the suffix ate. And similarly, if we start to have fewer oxygen atoms compared to our reference acid, the us acid suffix turns into ite as the suffix. And so it's similar, but the suffixes are a little bit different. And so you'll have to keep it distinct in your mind that acids, those neutral compounds, have ic acid and us acid as their suffixes. And oxoanions, those anionic species with charges associated with them, are going to have ate and ite as their suffixes. For the number of hydrogens, that's a little bit easier. You just have to look at the absolute number of hydrogens that our anion has and name it appropriately. If you see that your oxoanion has 2 hydrogens, call it dihydrogen. If you see it has 1 hydrogen, there's 2 equivalent names that you could use. You could either say hydrogen or you could use the prefix bi. And if there's no hydrogens, you don't say anything at all. But what if you happen to have the same number of hydrogens as your acid? You gotta stop immediately. That means that you have an acid, not an oxoanion, because that's going to be a neutral compound. And so you want to go back to your naming scheme for oxoacids. And so there's one other category that we have to figure out for an oxoanion, and that's to figure out what the charge is going to be. So the charge rules for oxoanions is the difference between the number of hydrogens in your compound versus the number of hydrogens in the reference acid. Pretty neat. So that's a lot of new information, and so let's go ahead and practice this. Go ahead and I'll do the first example, and then we'll see if you can do a little bit of practice with the second example. The first thing that we want to do is we want to try and name an oxoanion that has the chemical formula HCO3-. All right, so with my reference table at hand, let's see if we can go ahead and name this compound. The fact that I see that this has a negative charge lets me know that this is an oxoanion, and so I don't need to name it according to the oxoacids. I get to use the information on this slide to name the compound, but it's always good to double check. The next thing I need to do is I need to apply my hydrogen rules. I see that this compound has 1 hydrogen, so I could name this compound starting with the word hydrogen or with the prefix bi. And either of those would be just fine. Next thing I'm going to do is I'm going to figure out how to name the compound based on the number of oxygens. I see that my reference acid, carbonic acid, has 3 oxygens, and so does this compound. And so since I have the same number of oxygens, I'm going to use the root word carbon, and then attach the suffix ate. So far we've got hydrogen carbonate. And then I can go ahead and just double check and make sure the charge makes sense. Because I'm going from formula to name, not name to formula, I don't have to determine this myself, but I want you to notice that this compound has 1 hydrogen versus the 2 found in carbonic acid. And so that difference, 2 minus 1, is where we get the -1 charge from. So once again, this compound is going to be named hydrogen carbonate. Alternately, you could call this compound bicarbonate. Now let's do a second example, and we'll have you pause the video and see if you can figure this one out on your own. What would be the chemical formula of a compound named biphosphate? All right, so in this case, I'm going to see if I can go from my name to my formula. The first thing I notice is that I have the root word phosphate showing up in this compound. So I know that whatever else happens, this compound is going to involve a phosphorus. Next, I'm going to see how many oxygens are present. I notice that I have the suffix ate, and I don't have the suffix per. So I know that I have the same number of oxygens compared to my reference acid. Here, my reference acid is phosphorus acid, and so I see that I'm going to need in biphosphate 4 oxygens. Again, that's because all of my naming rules are with respect to these reference acids. So I figured out the number of oxygens. I also now need to figure out the number of hydrogens, and I see that the word bi, or this prefix bi, tells me that I need a compound with 1 hydrogen. So last but not least, I need to figure out the charge that's present on biphosphate, and this is where I'm going to compare the number of hydrogens in my reference acid to the number of hydrogens present in my current compound. In this case, I have 3 in the reference acid and 1 in my current compound, and so the difference between that 2 is what's going to tell me that I should have a charge of 2- on this compound. And so the chemical formula for biphosphate ends up being HPO4 2-. All right. So let's go ahead and do an example of how these oxoanions show up in ionic compounds. MgSO4 is going to be our example. And so once again, we're going to try and walk through this flow chart and take this small chunk by small chunk in order to determine what our name should be. All right, first step, do I see a metal in the compound? Absolutely. Magnesium, element 12, is a metal. Is the metal a transition metal? No, not in this case. However, I see that I have 3 or more elements showing up. And so what I'm going to need to do is name the metal first, followed by the polyatomic ion second. And in this case, I'm not going to change the ending to "ide." I'm just going to name what that polyatomic ion is. So I'm going to have to use my rules for oxoacids in order to name the second piece of this compound. All right, in order to do that, I probably need to figure out what SO4 and its equivalent charge corresponds to. I know that Mg is going to have a 2+ charge, so for this compound to be neutral, which it needs to be, that means that it has to be SO4 2- that I'm dealing with. And now I can try and figure out, using my rules for oxoanions, what this compound should be named. I know that the sulfur showing up means that my root word is going to be sulf. I also, if I look at my table of reference acids, see that the number of oxygens present is the same as my reference acid. That lets me know that this is going to be sulfate. If there was hydrogens present, like it was MgHSO4 of some sort, then I would need to explicitly name those hydrogens as a prefix in front of my oxoanion. But because there's no hydrogens, sulfate ends up being the full name of this particular oxoanion. And so using this flowchart, I see that my name is going to consist of the metal first, magnesium, followed by the name of the polyatomic anion, sulfate. And so my full name for this compound is magnesium sulfate. All right, the very last thing that we need to talk about for today in order to fully wrap up our discussion of polyatomics is to talk about something called hydrates. Hydrates are compounds with one or more water molecules associated with that compound. And in terms of notation, hydrates are denoted with a center dot between the compound and the water. So for example, if I wanted to talk about a hydrate of MgSO4, remember, that's magnesium sulfate, I'm going to attach a center dot in between MgSO4 and the waters that are associated with this compound. So you might see something like MgSO4 dot 7H2O. How we name this is that we say the name of the original compound, and then we affix a suffix to the end of the compound name to indicate how many waters of hydration are associated with the compound. We use the same prefixes to indicate numbers that we did with covalent compounds, and then the word hydrate is what we use for H2O. So in our example of MgSO4.7H2O, how we would name this compound would be magnesium sulfate for the reasons that we discussed on the previous slide, hepta for 7, hydrate. So magnesium sulfate heptahydrate. All right, so that ends our discussion and our lecture for today. We talked through binary compounds, not only how to name covalent and ionic species, but also how to think about binary acids and simple organic compounds with a focus on alkanes. Next, we talked about polyatomic compounds, and we saw that even though there's a set of common polyatomic ions that we have to memorize, the rules for oxoacids and oxoanions means that they're fairly systematic and don't have to be the subject of blind memorization. And so with that, what I'm going to leave you with for your pre-class assignment and something that we'll discuss when you come to class is how to name additional compounds. Because once again, this is a subject where we need to do a lot of practice to reinforce how to use this flowchart and what situations we use for different naming schemes. So it's time for you to practice. Try and fill out this table to the best of your ability, and we'll discuss this when you get to class. Thanks, everybody, and I look forward to seeing you come Wednesday.